Here we go. Right. So question 1. The diagram shows a sector AOB of a circle, centre O, radius 12. The reflex angle AOB is 4.2 radians. Find the perimeter of the sector. Well, all we have to remember is when they use the word perimeter here, we're meaning the whole distance around the outside. So we've not just got the arc length to deal with, we've also got the radius. There would be twice involved in this. So the perimeter, part 1, is the arc. And we've learned that the arc length is r theta, so that is 12 times 4.2, because it's already given in radians. But then we've also got to add on the radius twice. And that, I think I've done this earlier, that gives us 74.4 centimetres, I think. There we go. And that seems to me like an awfully easy 3 marks to start the paper off. But that's all there was to it. You've just got to, it's just about knowing the formula, isn't it? And knowing that we need this to be in radians, because it is in radians. Fine. The area of the sector. Okay, well, the sector is, it doesn't matter that we've got this angle greater than 180. The area is just a half times the radius squared times theta. So it's just a case of carefully putting it into the calculator. And it comes out to 302.4. There it is. What a great 5 marks to start on that paper. We all happy with that? So we will go, we'll press straight on without even pausing the video. Do some of that editing stuff later. Oh, wow. Into question 4. So that was using our arc length area of the sector stuff. We've now got the diagram shows 2 points A and B on a straight coastline, with A being 2.4 kilometres due north of B. A stationary ship is at point C on a bearing of 40 degrees and at a distance of 2 kilometres from B. And we've got that marked on the diagram. It's all there. Find the distance AC, giving your answer correct to 3 significant figures. So actually this is not, away from all this bearing stuff, this is just, there is a triangle. We've got an angle on 2 sides, and we need to find the 3rd side. Well, if you think of the whole sine and cosine rule that we wrote down, all of that stuff, then the sine rule, if you're in here, you would either need to know 2 angles, or to be dealing with 2 angles, to have one to find the other one, to use the sine rule, whereas the cosine rule is all about 2 sides and an angle. B, C, A, or A, B, rearrange it, whatever. So that's there. We're perfect for the cosine rule. It's on the formula booklet. It's even arranged in the right way for the cosine rule. So we'd be doing AC squared is 2.4 squared plus 2 squared minus twice 2.4 times 2 times the cosine of 40. Now, of course, in this case you didn't have to, because the first question didn't involve sine, cos or tan. But in the first question you may have been tempted to put your calculator into radians mode. It's a radians mode. You need to make sure that you turn your calculator back into degrees for this one, so that when you type this into your calculator you're going to get the right thing. So checking that the calculator is in degrees, this I think should give you 2.405 as being the value of AC squared. And then when we square root that, we get AC is 1.55 kilometres to 3 significant figures. Of course, hopefully we've got it firmly drilled into us now that whenever you square root, you should write plus or minus. Because it's a really common mistake in Core 1 especially, that we forget to write plus or minus. But here's here's kind of the exception to that, because we're dealing with distances, and when we're talking about the distance from A to C, it's got to be a positive value, hasn't it? It doesn't make sense for that to be negative, so it's fine to neglect the plus or minus and just go straight to the answer. Right, part 2 said, find the bearing of C from A. Now that actually means the bearing of C from A is we need to know what that angle that I've just marked in the diagram is. So you measure a bearing from north, don't you? Round in the clockwise direction. But first, in order to do that, I think we're going to work out that angle, aren't we? That would make sense to do that first. And if we think about how we might go about this, well there, we found that length. That length is 1.55 to 3 significant figures. So here we've got an angle on the side opposite, an angle on the side opposite. So this is straight into the sine rule now. So we're going to say that sine A divided by the side opposite it, which is 2, equals the sine of 40 divided by 1.55. But one thing that we're going to do that is going to be quite smart in this is we're not going to type 1.55 into our calculator. We're going to make sure that when we did this question here, and we got 2.405 and then square rooted it, that we either save that as a memory or we use it as the recorded answer in our next bit of calculation. It might be sensible to save it as a memory. Most of you have kind of Casio, recent Casio calculators. And so to save it as the memory, you have it as the answer on the screen. You press Shift and RCL, and then you choose one of the pink letters, A to F, I think, above the function keys, and store it in memory. And use that. Then you just use alpha and that letter in your next calculation. And we're going to make sure that we do that, because we're not going to use rounded values in our calculation, because it brings in rounding errors. If we rearrange this, we get sine A is 0.8288, I think. If you use the exact value, check that you can agree with that. And then inverse sine of that gives us A is 55.98 degrees. But of course that's not our answer, is it? So the bearing that we want is 180 minus that, because remember, we want that red bearing. If that's 55, did we say? 55.98, then take it away, and we get 124 degrees to 3 significant figures. Okay? It's really important that you get to use good calculator memories, that you know what you're doing with that, and remember how to put things in. This is bearing. Was that the word that you were looking at? This is bearing. Look, bearing. I mean,
35.
Yeah, well, ignore it. Yes. That's not mentioned. Okay. Last part 3. What does this say now? Find the shortest distance from the ship to the coastline. Well, the shortest distance from the ship to the coastline is if you take a perpendicular line from the coastline to the ship. That would be that distance there. And so what we need to do is now think about this as a right-angled triangle now. We've got some things that we know about already. We know that this length is 2. There's the ship. That's the point that we're interested in. There was B. That's 40 degrees, although you could take the other right-angled triangle at the top. We need to find the length PC. Well, this has just gone back to being old-style Sokotoa type stuff. We need to find the opposite. We've got the hypotenuse. So we remember how to do this. This would be sine of 40 is opposite over hypotenuse. So if we rearrange times that, we get PC is 2 sine 40, which was 1.29. Okay. You could have done that with the other right-angled triangle, the one that's up here, using the bits that you know about that triangle up there. But it's more exact because we had to calculate all the bits, whereas this one we were given in the question. So that makes more sense. Right. Any questions about that? It's all gone right so far, hasn't it, this trigonometry stuff? Are we ready to go on into the last question of trigonometry? This is a little bit fiercer. So I said it was the square numbers. We've had 1, we've had 4. So that makes the next one 9. Good knowledge of square numbers there. Well done. Right. So. Right. So here we have sketch the graph of y equals tan half x for x between minus 2 pi and 2 pi on the axes provided. On the same axis, sketch the graph of y equals 3 cos a half x for minus 2 pi to 2 pi, indicating the point of intersection with the y-axis. Right. Well, one of the things to remember is that transformations of graphs is one thing that appears on all of the core modules. Core 1, 2, 3 and 4 all include transformations of graphs. I haven't written out the rules of transformation. Hopefully you recapped them this morning in the core 1 thing, so we can remember hopefully some of the things that happen. So let's think through, before we draw anything, what's going on with some of our graphs here. The first one, tan half x. Well, the half there has the effect of, well, what can you remember? What effect does that have as a transformation? It stretches it in the x direction, doesn't it? It makes everything, it will be a stretch, scale factor 2, parallel to the x-axis. So that's the first bit, that's what tan of a half x is. It's like tan x, but stretched. Okay, so that gives us an idea of what we're doing for tan. If we can draw the tan x, we can draw tan a half x. 3 cos a half x. Well, that's 2 transformations happened at once there, but it's okay because they're perpendicular directions, so they don't interfere with each other. The half x one is again it's going to be a stretch that direction, and the 3 is going to be a stretch scale factor 3 in the y direction, parallel to the y-axis. So we've got both things happening for 3 cos a half x. It's a stretch scale factor 2 parallel to the x-axis plus a stretch scale factor 3 parallel to the y-axis. Right, I feel that I'm about ready to draw these. So I'm going to start with the tan graph. In the formula booklet, in the answer booklet, you were given axes that looked a bit like that, but they did have really kindly marked on them minus 2 pi, minus pi, pi and 2 pi. So they were already marked on the set of axes you were given in the answer booklet. There was nothing marked on the y-axis. And the nice thing about that is that if our normal asymptotes for tan are at pi by 2 and 3 pi by 2 and minus pi by 2, then if we stretched it, our asymptotes would now be there and there at minus pi and plus pi. And so the tan graph that would normally be quite compact around there is just going to be spread out a little bit more. And it's going to be going like that. So that is tan half x drawn to start with. The other one was the cos graph in the same range. Now remember, because frankly, if it hadn't been stretched, we'd be doing the full bit in that 2 pi range, but it's not because it's been stretched further. So we're going to start up here somewhere, and we're only going to get down to the bottom bit by there, and it's going to cross at pi, because it would normally cross at pi by 2, and it's stretched, so instead of pi by 2 it can go to pi, and it's going to do the same on the other side. So this one is going to go, I get this, oh, it's a little bit dodgy, there we go. That's alright, isn't it? And then it would keep on doing that over and over again. And it was scale factor 3, wasn't it? So that's at 3, and that's at -3 down there. And there we go, it's up like that. They gave plenty of marks for that, didn't they? No, not really. 3 marks for that. So it's a little bit mean. Now, the next bit of the question says, show that the equation tan half x equals 3 cos of half x can be expressed in the form that. So we talked about quadratics before, we're back to them.
It says you need to show the points of intersection. Oh, with the y, sorry.
With the y, yeah, I've done that, sorry.
I thought it was between the two.
No, it was just with the y-axis thing. Actually, we've got the points of intersection with the x-axis. Okay, so show that tan of half x equals 3 cos of half x can be expressed in that form. Right, well, let's do it. Part 2. Tan of half x equals half x equals 3 cos of half x. Right. Now let's think, where are we heading for with all of this? We want to get something that only involves sine half x. So that's got to be our focus. Let's keep that in our mind. We're aiming for sine at the end of this. Well, the first thing that we can do, there's not a lot we can do with cos, but using those identities that we wrote down, tan is sine over cos, isn't it? So that is sine of half x over cos of half x. We want to try and just go and work with this. So let's take the cos of half x that's on the bottom there and multiply both sides by cos of half x. Seems sensible. That gets rid of it from the bottom. We're left with sine of half x. And over here, 3 cos of half x times cos of half x would be 3 cos squared of half x. Now, I just in passing didn't do much with the second identity. I was thinking I probably should have expressed that in another way. So if we go back a second, way back to here, we had, one of the last things we wrote there was this. Now that's the identity, that's how you remember it, but it might be worth saying, we can also write that as being sine squared theta is 1 minus cos squared theta. That's also true, isn't it? If you take cos squared away from both sides. And cos squared theta is 1 minus sine squared theta. And it's easy to derive those from that start point, but it's worth remembering that we've got those ways that we can write sine squared and cos squared in other forms. So if we go back to our question, we're now going to say we're still, in our mind, we're aiming for everything in terms of sine. Here we've got 3 cos squared, so that's going to be 3 lots of 1 minus sine squared of half x. And now we're making some progress with this, because that is sine of half x is 3 minus 3 sine squared of half x. And I'm hoping if we take everything to the left-hand side, that's what we're supposed to be aiming for. Is that where we're supposed to be getting to? It is, isn't it? Wow. But that's not what we've done. Because if z and can solve it for x in the range minus 2 pi to 2 pi. So we need to solve this. How many times we're going to use the word quadratic today? Which is a quadratic equation again. It's a quadratic in terms of sine, a half x. You may feel happier writing it as being 3, what can we use, t squared, plus t minus 3 is 0, I'm thinking about writing it like that. Now this is a little bit mean, because this one, we could try that trick of multiplying first and last thing together and get minus 9, but there's no two things that multiply to give minus 9 that add to give plus 1. This doesn't factor this. So bearing in mind that it doesn't factorise, you've now got other choices. You could try and complete the square, but that's a slightly later thing to do, because completing the square isn't that easy. But you have the quadratic formulas come up with one, haven't you? Yes. So, we go straight into t is minus b plus or minus the square root of b squared minus 4ac. 1/2a. Okay, which gives us, well, throw that into calculator. Well, actually, it comes out as being, I think this is right, minus 1 plus or minus the square root of 37 over 6, which just confirms that it didn't factorise. So we have minus 1.18 and 0.847 as our roots of our quadratic. Now, at the moment I'm just kind of focusing on t, but that's a bit daft because t I invented. I didn't invent t, introduced the letter t, and so we get, that'll be a ludicrous claim, isn't it? And then on the internet, I invented t. I'm the king of England. So we have two values that sine could be. Sine half x is minus 1.18 or 0.847. Aha, but we know that sine of anything can't be outside the range minus 1 to plus 1, because sine just goes plus or minus 1 all the time. So this has no solutions. We can ignore sine of half x equals minus 1.18 because it can't possibly be true. Which leaves us with sine of half x is 0.847. We now need to solve that. Right. We've got to be in radians. That's a added complication to this. If we do inverse sine of 0.847, can you see what's happened in this exam paper again? Question 1, in radians. You didn't need to do sine cosine, so you probably didn't change your calculator. Question 4 was in degrees. You had to find both sine and cos of an angle in degrees. So your calculator had to be in degrees. Question 9, we're back to radians again. We have to be working in radians because it's between, it said it was between minus 2 pi and 2 pi. So, inverse sine of 0.847 half x. Your calculator says, it should say, 1.01. Okay. Now it turns out to be not that big a deal of working it out. If you're like Dave and you like the cast diagram, at this point you think, we've just done a sine of a positive thing. Sine of positive things are in A and S quadrants. So that means this angle here is 1.01 according to my calculator. So the two angles I'm after are 1.01, and the second one would be, if I measured round from there to there, that is 1.01 less than pi. So my second value is pi minus 1.01. If you don't like the cast diagram, or at least think what is all this cast diagonal nonsense? Give me a nice sine graph. There's the sine graph. We've just done inverse sine of 0.847, which is up here somewhere, fairly close to 1. The calculator's just told us that that value there is 1.01. Using the symmetry in the graph, because it's symmetrical around pi that's there, if that's 1.01, that must be 1.01 as well. So the angle is pi minus 1.01, and you get it the other way just the same. Whichever way you do it, whichever way you choose to do it, you get those two values. We are looking for, answers in the range minus 2 pi to 2 pi. So a half x is from minus pi to pi. So actually, we should have been considering over this bit of the graph as well, shouldn't we? But it's all right because it doesn't come back in that range to give us any values. They're the only two that we get in the range minus pi to pi. They're the only two in the range minus pi to pi. So that's it. Finally, what we're going to do is we're going to double those two answers. So x times that one by 2, we get 2.02. Pi, take away 1.01 is, what's that, 2.13, which doubled would be 4.26. And then we could write radians at the end of that, or we could put the little c to show that it's in radians. There we go, both to 3 significant figures. Bit of a mammoth question. Worth 9 marks. What we did there, it wasn't actually that much for 9 marks. 2.02 is half that, then x is twice that. And that one came out to being 2.13. Okay, are you ready with the camera? That's which one you get to stop that video.